So here's a first improper integral to consider, the integral from 1 to infinity of 1 over x dx. And first to discuss, improper integrals in general. I think it helps to visualize these in terms of area, especially for a function with positive values like this. So the graph of y equals 1 over x, you might recall, looks like this, something like this in the first quadrant. And then it's got, this guy down here in the third quadrant. So if we're evaluating the integral from 1 to infinity, let's say here's 1, and when x is 1, y is 1 with this function. And so we're evaluating this thing from 1 to infinity. So the curve approaches its horizontal asymptote at y equals 0 here. So if we're thinking about that in terms of area under the curve y equals 1 over x, which let me label that, then it's the area from when x equals 1, that's your lower limit of integration, to, as x approaches infinity. So the integral, that improper integral represents the area of this unbounded region. So the region extends forever out to the right here. Okay, so if we really want to write an integral that represents, area of a finite region, then what we could do is set up some kind of right-hand boundary here, and I'll call it capital M, since that's the way I have it labeled in the notes. And so we could write the integral that finds the area under the curve 1 over x going from 1 to m, and then take the limit as m increases out this way. So take the limit as m approaches infinity. And so this is the way we express an improper integral as a limit of a definite integral here, where m is some finite number that's increasing without bound with this limit here. Okay, and so that's the way we actually evaluate this. But so in terms of thinking about it physically, before I move on, so we're finding the area of this finite region from 1 to m, and then as m increases, so imagine you make a table showing the area under the curve as x goes from 1 to 100, and then the area under the curve as x goes from 1 to 1,000, and you continue this way. Then you look at the value of the area of that finite region and see if it's approaching some fixed number. Okay, but so the way we can evaluate this, we're using fundamental theorem of calculus. So we would first translate it to a limit, like I described below. So the limit from 1 to m, as m approaches infinity, of 1 over x dx. Now I know that the antiderivative of 1 over x, so a function whose derivative is 1 over x, is natural log of x. So this is equal to the limit as m approaches infinity of the antiderivative, natural log of x, as x goes from 1 to m. I'm not putting the absolute value around the x here because I know that x is positive in this interval. And so this is the limit as m approaches infinity of natural log of m minus natural log of 1. Natural log of 1, this is a useful fact, is 0. It's good to remember that. So we really just need to evaluate the limit as m approaches infinity of the natural log of m. So here's where it helps to recall the shape of the graph of y equals natural log of x, which is natural log of x is an increasing function with a domain from 0 to infinity and a vertical asymptote at x equals 0. So as m approaches infinity, or in this case as x approaches infinity, natural log is an increasing function. It's a very slowly increasing function, but this thing is always creeping upward. So as the argument here approaches infinity, the value of your natural log also increases without bound. So this is approaching infinity. When the value here is approaching infinity, that means it's not approaching some finite number. If we wrote a table showing the area from 1 to, like I said, 1 to 100, from 1 to 1,000, the area would just be increasing without bound. It's not approaching anything. That's what this tells us here. And so the integral from 1 over x, the integral from 1 to infinity of 1 over x dx here diverges. Okay, so 1 over x diverges. I want to compare that with 1 over x squared. Because the graph for that function, this, is similar. So we know that this one diverges. Box that out. So example 1b was the integral from 1 to infinity of 1 over x squared. Which if you graph that, and I actually have, this is very low tech. Sorry. Graph this way I can generate your videos for this semester. But so in red there I have the graph of 1 over x. In blue I have the graph of 1 over x squared. So 1 over x squared, they're both approaching this horizontal asymptote at y equals 0. But the blue is 1 over x squared. It's approaching that horizontal asymptote a lot faster. So if you think about the area under the blue curve, area under the red curve, from 1 to infinity, so as your right-hand boundary slides out this way, notice that you've got a much smaller area. As you creep out towards infinity, much smaller bits of area that you're adding under the blue 1 over x squared graph compared to the red 1 over x graph. So let me zoom that out there. Okay. So there's something to that. So the graph looks similar, because my hand-drawn graph is going to look pretty much exactly the same here. But I wanted to show you the difference there. There is a difference here. So if we're thinking about it in terms of area, then this one's approaching the y equals 0 much quicker than our previous graph. So there's going to be an impact there. But the way we set it up is the same way. So set your right-hand boundary, call it m or t or whatever you want, and then turn this into the limit as that right-hand boundary approaches infinity of the integral from 1 to m of 1 over x squared dx. Okay, now integrating 1 over x squared. Let me do that work down here. So the antiderivative of 1 over x squared, we would use the power rule. So that's the antiderivative of x to the negative 2. And if you use the power rule to write the antiderivative, that would be x to the negative 1 over negative 1, which is equal to negative, I'll just put the negative out front, and then x to the negative 1, so that's 1 over x. So going back up here, that means that what we're looking at is the limit as m approaches infinity of our antiderivative is negative 1 over x as x goes from 1 to m. Okay, so we can substitute in the m here. Evaluating the limit is the very last thing you do. So first we set it up as a limit, we find the antiderivative, now we plug in the values. Evaluating the limit comes at the very end. So now I would plug in m, negative 1 over m, minus negative 1 over 1. Okay, so this is the limit as m approaches infinity of negative 1 over m plus 1. And the limit of a constant is just that constant. So this 1 isn't really inside that limit anymore, just this 1 over m bit. Okay, but so this right here, so thinking back to the limits you did in 5.6, 1 over infinity, that's approaching 0. Any limit of the form finite number over infinity is going to 0. So this is equal to 0 plus 1. So in this case, the area under that curve is approaching 1. So while the integral of 1 over x dx from 1 to infinity diverges, 1 over x squared actually converges to 1. That would be our final answer for example 1b. And let me just end by showing the difference one more time. So the red curve is 1 over x. The blue curve is 1 over x squared. Notice how, so they're both approaching 0, which is a promising sign if we want the area as we move out this way to approach a finite number. Turns out the red one is not approaching 0 fast enough, but the blue one is. So the integral from 1 to infinity for the red curve diverged. The integral from 1 to infinity for the blue curve converged to 1. So there's something to that about how we want the value of the function to approach its horizontal asymptote, and not just that alone is not quick enough or not good enough. It needs to approach the horizontal asymptote quickly, which the 1 over x squared function succeeds in doing.